Alright, so today I'm gonna be explaining this important paper with the title All Nodes Are Created Not Equal. Node-specific layer aggregation and filtration for graph neural networks. This paper in 2024 for an IEEE transaction on knowledge and data engineering. The ever-designed graph neural network, though opening a promising path for the modeling of graph-structured data, unfortunately introduced two daunting obstacles to their deployment on devices. First, most of the existing GNNs are shallow, due mostly to over-smoothing and gradient vanish problem as they go deeper as convolutional architectures. And the second is the vast majority of GNNs adhere to homophily assumption, where the central node and its adjacent nodes share the same label. This assumption often poses challenges for many GNNs working with heterophilic graphs. Addressing the aforementioned issue has become a looming challenge in enhancing the robustness and scalability of GNN applications. So in this paper, they took a comprehensive and systematic approach to overcoming the two aforementioned challenges for the first time. They propose a node-specific layer aggregation and filtration architecture. They call it NoSAF. Node-specific. A framework capable of filtering and processing information from each individual nodes. So NodeSAF introduces the concept of all nodes are created not equal into every layer of deep network, aiming to provide a reliable information filter for each layer's nodes to sieve out information beneficial for the subsequent layer. By incorporating a dynamically updated code bank, NodeSAF dynamically optimizes the optimal information outputted downwards at each layer. This effectively overcomes heterophilic issues and aids in deepening the network. To compensate for information loss caused by a continuous filtering, we also propose NoSAF-D, which incorporates a compensation mechanism that replenishes information in every layer for the model, allowing NoSAF to perform meaningful computation even in very deep layers. Challenges in GNN architectures. We have limited node discrimination and skip connections, and inadequate handling of heterophilic graphs. So this is the basic pipeline of NoSAF. So the model X, input X, is fed into a mapping zeta. Is typically just an MLP. So we have this hidden representation. The encoded feature serves as input to GNN, and the input dimension for each subsequent layer is uniformly deep. And of course they do batch normalization, and then here after that GCN block employs batch normalization and nonlinear activation function ReLU, denoted as sigma, to shape the output expression of each layer. So this Z, it represents the complete expression of all nodes at the else layer. So we implement two modifications to ensure that NoSAF can adaptively address both the challenges of heterophilic graphs and the need for deep network layers, effectively killing two birds with one stone. So to better preserve the updated state of each node at every layer, we introduce a dynamically updated code bank. So given the code bank CL and the node feature Z at layer L, we utilize the values in the code bank to gauge the importance of aggregated information. So we have a dynamic filter for each node. It learns specific information that should be retained for each node. So let's call it node weight. So first, concentrate on the significance of nodes across different layers. With the hybrid beta I, we generate weight for node I like this. And they use a leaky ReLU with a negative slope of lambda. And then they finally calculate this score, this importance score, which is between 0 and 1, because of this sigmoid, of course. By assigning the corresponding score as filter to each node, we can dynamically update each node's contribution to the deeper layers of the network. And we denote this filtering operation like this. So this is the model overview of NoCef and NoCef-D version. NoCef assigns weight gamma, and it is dynamically update the code bank to ensure that the most optimal information is retained. So you give the node model, you have the representation, you give it to the filter, then you have your GCN blocks. Now here you're using filter. You add, and this is the code bank that the filter has initialized, the code bank space. We project it, it becomes like this, then you give it to softmax, and then you compare it with ground truth using this loss, cross entropy loss. So how do we do this code bank updating? The filtering mechanism applies weight between 0 and 1 to the aggregated information of the nodes, reducing the amount of noise accumulated in the code bank and diminishing many meaningless aggregations. So we introduce a dynamically updated code bank to iteratively refine the information, ensuring the final update yields the optimal output. Assume that the updated state of the code bank is denoted as CL. We summarize the layer-wise update formula like this. We use the information in code bank from the last layer as the representation learned by the backbone network. We summarize it like this. The final updated code can be represented as the sum of filtered information across all layers. We use a mapping layer zeta to extract features from C and map them to dimension K, and K represents the number of classes for classification. The model is then trained using cross-entropy loss. And then they try to deepening their model of NoCef. They call it NoCef-D. So this is the framework of NoCef and NoCef-D. So if there is no deepening, you use NoCef. But if you have NoCef-D, then you also update this. You add this loss. And finally, you calculate eta. You update network weights. So they did experiments on Cora, Sightseer, Squirrel, Chameleon, and other datasets. They compared state-of-the-art like graph convolution, graph attention, and other methods to their methods, both deepening and the normal one.